I want to thank again for the organizer to invite me to do this talk. I'm very excited to be here, and I hope you will be excited by my talk. So and as I hope it's not too much quantum today. So what I'm going to do today is I'm going to introduce a discrete quantum walk model called bipartite walks. And later I will introduce a concept called the Hamiltonians, and I will use these Hamiltonians to build a connection between the bipartite walks and continuous walk. And first, what is a discrete quantum walk? So for the purpose of our talk today, I just give a very easy definition of discrete quantum walk. A discrete quantum walk is determined by a unitary matrix U, which we call the transition matrix of our talk. And then we usually use the vector EI to denote the initial state of our quantum walker. And then the probability of our walker is at the state EJ at k step is the norm square of the ij entry of U to the k. And one application of this discrete quantum walk is very famous Grover's algorithm. And Grover showed like how you implement this setup can be used to enable a quantum computer to do a search over a database that is way much faster than any known classical algorithms. So we know it's a very useful and important quantum walk model. And then now I'm going to show you like one discrete quantum walk model that is called bipartite walks. So to construct a bipartite walk, first we need a bipartite graph. So given a bipartite graph, we know you have two color classes. So just using the example here, we have two color classes. That is the pink one and then the green one. So right now we have two classes of our bipartite walk, of our bipartite graph, and then we can partition our edges into two ways based on each of the color classes. So we say if two edges have the same end in this pink vertex part, if they have the same end here, then they will be in the same cell of our partition pi 0. Similarly, if they have ends that is the same in this green partition, have the same green vertices, and then they will be in the same cell in our partition pi 1. So that's the example I'm showing here. And then the one marked with the triangle will be in the same cell in our partition pi 0, and then the one marked with squares will be on the same cell in pi 1. And right now we have two partitions, right? So based on these two partitions, we can have two characteristic matrices that corresponding to our partition pi 0 and pi 1. We call it P0 and P1. So basically what is a characteristic matrices is like we just index the row of our P0 to be the edges of our graph, and then each column is indexed by the cell of our partitions. So right now we have two characteristic matrices, and then we want to use these two to get a projection to get two projections. So what we do, we normalize them. So what it means, basically, we take the column vector of each matrices, and then we just scale them into a unit vector, and then we get this two normalized P0, P1. And then we use these two normalized P0 and P1 and get two projections, P and Q. Those P and Q will be projections that is constant on the cell of each partitions. So it will be constant on the cell of pi 0, and Q will be constant on the cell of pi 1. So right now we have two projections. And then based on these two projections, we can get two reflections. Because PQ are projections, 2P minus I and 2Q minus I will be reflections. And then we just take the product of those two reflections, we get our transition matrix U for our bipartite walk. And that's the example of the transition matrix we get using the bipartite graph I just showed you before. And right now we know what is discrete quantum walk, and we know a model of it, a bipartite walk. So what is next? So the next is continuous quantum walk. So I'm going to define that over a graph. So a continuous quantum walk on a graph G will be described by its transition matrix u to the t, and t is the time here. So it will be writing as exponential times ith, and h is just some suitable Hermitian matrix that is associated with G. And like Sophia's talk this morning, she used adjacency matrix of G, and some other common choice of H will be like Laplacian of your graph G. Okay, so right now I'm going to introduce the Hamiltonians of bipartite walk, and I use that to build a connection between discrete walk and continuous walk. So we know, like for every unitary matrix U, there will be a Hermitian matrix H, such that you can be written as exponential times IH. And then such H we call a Hamiltonian of U. And because our U is unitary, we can have its spectral decompositions. So which means if e to the I theta r is the eigenvalue of U, and then we use ER to denote the eigenmatrix of e to the I theta r, then we can have the spectral decomposition of U writing as such here. And then we just take the logarithm of U, and then we get our H, the Hamiltonian of U. But we know that because depends on how we take the logarithm, our H, the Hamiltonian, is not unique. So if we restrict the angle to be between minus pi and pi, and then we call the resulting Hamiltonian the principal Hamiltonian of U. And then for our bipartite walk, we use this principal Hamiltonian of U to be the Hamiltonian of U. So before going any further, I want to introduce like two matrices. One is like skew adjacency matrix. That is like given an oriented graph G, and then we define the skew adjacency matrix to be a skew symmetric matrix such that if the ij is equal 1, that means there's an arc from I to j, and if there's an arc from j to I, then we put -1 into the ij, otherwise we put 0. And here is an example of oriented P3, and that's the skew adjacency matrix of P3 here. And for our weighted oriented graph, so the skew adjacency matrix for weighted oriented graph, we put the weight of the arc instead of 1 into each corresponding entries. So here is the skew adjacency matrix of weighted P3. And we can see if a Hamiltonian is of the form H times IS, where S is real skew symmetric, and then it will corresponding to a skew adjacency matrix of a weighted oriented graph. And we call this weighted oriented graph H digraph. And we can see like if H can be, if our bipartite walk can have a Hamiltonian that is of the form I times S, and then as a skew symmetric, then the walk will be equivalent to a continuous walk on the H digraph over integer times. And just going back to our examples, and if that's the bipartite graph we have, and then this will be the Hamiltonians we have, and then that's the corresponding H digraph. So right now we want to know when can we get a H digraph that is coming from our bipartite walk. So I can show that if let U to be the transition matrix of a bipartite walk on our bipartite graph G, and then let H to be the Hamiltonian of U, and then we can write H as the sum of I times S0, where S0 is real and skew symmetric, and plus pi times E-1, where the E-1 here is the -1 eigenmatrix of U. but this E-1 eigenmatrix will be real. So if we want our bipartite work to have an edge digraph, which means we want to eliminate the E-1 eigenmatrix, which means we want the dimension of the -1 eigenspace of U to be 0. So just use this idea, I can show that if our bipartite work can have an edge digraph if and only if the adjacency matrix of our bipartite graph is invertible. So right now we have all the machinery we want, and we will use them to build a continuous quantum work that was a very interesting but also rare phenomenon called universal perfect state transfer. So first, we look at this very easy example of bipartite work over P8. And then that's the transition matrix of our bipartite work over P8. We notice that a transition matrix is actually a permutation matrix, and it has order 7. And this, we can extend the result to all the passes. All the passes will have very nice form. The transition matrix of bipartite work on the PM will have very nice form because it will corresponding to a permutation matrix. And then we know exactly how the permutation will look like. Will be look like this. And then since when n is even, like the adjacency matrix of PM will be invertible. So in that case, we will have the edge digraph. And then the edge digraph will actually corresponding to an oriented Kn-1. Now we know the information we need. We are going to build an example of continuous quantum work with universal perfect state transfer. But first, what is perfect state transfer? So we say if we define the continuous work over graph G and then let U to be the transition matrix, and we say there's perfect state transfer from EA to EB at time t, if and only if the norm square of the AB entry of U to T is equal 1. So yeah, there are actually like two forms, depends on your work is discrete or if it's continuous. So just, yeah, going back to our usual example here, we can see this like 1/6 entry have the 1/6 entry of U will be 1. So which it means like after 1 iterations, if you start from E1, it will go to E6 with probability 1. So what is universal perfect state transfer? We say a graph has universal perfect state transfer if it has perfect state transfer between every pair of its vertices. So we can see here, like this is the transition matrix of P8. So we know it's a permutation matrix and it has order 7. So we know the continuous work over the edge digraph of coming from the bipartite work on P8 will have universal perfect state transfer. So what does it mean? It means like that is the K7, which is the oriented K7, which is edge digraph of the bipartite, like coming from the bipartite work on P8. And that's the Hamiltonians we have. So if we just assign the weight of each arc according to our Hamiltonians, then we do a continuous work over the resulting weighted oriented, like this K7, and then the work itself will have a universal perfect state transfer. And then I can give a formula for you to like assign the arc of each of you Kn-1, and then the resulting Kn-1 will have universal perfect state transfer. And this, we not only know like the work on the oriented Kn-1 will have universal perfect state transfer, we also know because the transition matrix on transition matrix of bipartite work on P8 will have order n-1. We know like perfect state transfer over this oriented graph, over our like edge graph, the perfect state transfer between any two vertices of that will happen within time t, and then t will be bounded above by n-1. Yeah, that's the fun and interesting result I want to show you guys today. Thank you.
Yeah, thank you. So, are there any questions or comments?